Hello everybody, my name is Felipe. Thank you for having me here. I'm from the Technical University of Berlin and today I'm going to present our work that is AdCom, an adaptive combiner for string aggregations. Here we explore the use cases for string queries on string data. Take for instance use cases such as maximum temperature alerts on dashboards or minimum price for stock markets. These use cases, in general, they consume data from string sources, which are ingested on string processing engines, such as Apache Spark or Flink. And string aggregation queries are executed on these SPUs, such as average, sum, count, maximum, median, and the results are exposed on dashboards to the end user. So under the hood, these use cases, we have to create some queries that are basically composed of two transformations, are grouped by any aggregate transformation, as we can see on the top query of this slide. These transformations are basically deployed on different task managers. As we can see, the subtasks A1 and A2 process the group by transformation in parallel. The data is exchanged on the shuffle phase to the next transformation, that is the aggregate transformation on the subtask B.1 and B.2. And here we calculate the maximum values, for example. As we increase the parallelism, the channels on the shuffle phase potentially increase. And as we increase the workload that is consuming, the data on the shuffle phase also increase. And as we expect, the shuffle phase is a common bottleneck on this string pipeline. Some nice optimization that is done is to add some pre-aggregate transformation, as we can see on the other query, that we aggregate locally every 5 seconds, for example. This potentially reduces the data on the shuffle phase. However, for string pipelines, this is not enough. This approach, also known as a combine plus reduce, is static. And for string pipelines, even when the workload increases, the shuffle phase could be still a bottleneck. And that is what we explored on this motivation example. We increase the workload, and at some point, the end-to-end latency starts to increase, even with a pre-aggregate transformation before the shuffle phase. A common solution is, of course, to restart the query with a new parameter on the pre-aggregate transformation. However, this is not desirable for string pipelines. So we devised this new transformation called AdCom, an adaptive combiner, which dynamically adjusts the time to pre-aggregate tuples before the shuffle phase. And the goal is to achieve the highest and sustainable throughput on the shuffle phase, and of course, without compromise the latency. And we use a proportional integral controller for this, that I would like to explain 3 basic steps. We need a controller to decide if we aggregate more or less tuples before the shuffle phase. On AdCom, actually, we need the proportional controller to decide how fast we adjust the pre-aggregation. For example, if we are pre-aggregate every 1 second, we might decide to aggregate every 2 seconds or 3 seconds based on the back pressure signals. And this, we can achieve a fast adjustment. However, when we are closer to the reference value, that is a medium back pressure, basically, the proportional factor cannot have a big difference compared to the reference value. So we introduced the integral factor as well, that is based on the previous values of back pressure signals. And with this, we can have fine adjustments on AdCom and also avoid some oscillation on the throughput. We implemented AdCom inside Apache Flink state-of-the-art stream processing engine nowadays. And basically, we consume data we consume back pressure signals from the AdCom subtasks. We decided based on the controller and on the proportional integral factor, the next parameter to pre-aggregate tuples at AdCom, and the actuator replaces this value on each UDF that is being executed at AdCom. And in the end, the solution, we could achieve the highest throughput, and we don't have to restart the query that is executing. And the developer just have to call this new operator AdCom as he or she was calling the group by or aggregate operator without passing the parameter, the local time we want to pre-aggregate tuples. On this experiment, we evaluate AdCom on consuming a workload that varies on the time. For example, we start with 50K records per second, then we change it to a 200K records per second, and we change back again to 50K. As we can see, AdCom could achieve highest throughput compared to the state-of-the-art pre-aggregate operator available in Apache Flink. And this is because the local global aggregate in Flink is based on two phases. First, it executes a mini batch based on time, and after it pre-aggregates values before the shuffle phase. And it's also static. In comparison, AdCom just has one phase that pre-aggregates based on the best time to pre-aggregate data before the shuffle phase. Next, we evaluated AdCom consuming data that is skewed, and actually the local and global aggregation available in Flink does a good job on skew workload. However, we still can see some oscillation on the highest throughput, and this is basically because at least one of the subtasks of Flink was in back pressure. In compared to it, AdCom had no back pressure, and the result is that we can achieve the highest throughput. And when we change the workload to a normalized workload again, AdCom spent about 20 minutes to adjust to the highest throughput. And this time it was because the AdCom was again adjust the time to pre-aggregate to a different workload. And we also evaluated AdCom on a common solution that everybody explore when we have back pressure. What is done is basically that they increase the parallelism of tasks. And here we can see that AdCom with only 8 reducers after the shuffle phase can achieve a higher throughput compared to the local global aggregation available in Flink, with not 8 reducers, but with 24 reducers. Of course, AdCom takes longer to achieve this throughput, but the point is that with less machine, we can achieve the same high throughput that Flink with local global aggregation is achieving with more machines. And of course, if we add more machines at AdCom, we can achieve this highest throughput faster. And with this, I would like to summarize our work. AdCom, an adaptive combiner that adapts to data rate variation and to different characteristics of the available network. AdCom is also resilient to skewed workloads, and we could achieve up to 9 higher sustained throughput compared to the existing baseline. And more important, we do not compromise latency. With this, I conclude. I would like to thank you, and I'm happy to take your questions.